Am I audible?
Yes. Akashi, you were saying something?
No, just yes, I was checking it. Okay, thanks.
Yeah, okay, Prashant. Hello, sir, welcome. I think our speaker has joined.
Hi, Sricheta. Good afternoon.
Yes.
How are you?
Yes, sir. I'm fine, sir. How are you, sir?
Yeah, I'm good. Sorry, I was on mute, so I think I was
Oh,
speaking,
okay,
but you
okay.
could not.
Okay,
Yeah,
sir, we will be
I'm good.
starting by 5 minutes. It's 10:25
Okay.
now. We will start on 10:30.
So should I share my slides?
So would you like
Or
to check? Then I can unshare my screen. Otherwise, we
I
will
mean,
give a short introduction of yours and then you can share your screen.
okay, no problem.
Okay, okay, sir. Thank you.
So this will be for 1 hour, right? Like the talk will be
Yes,
for
sir.
1 hour.
Yes.
Okay, and there
Yes,
will
sir.
be question answer after that.
Sir, if you would like to take the question answer in the middle of the session, we don't have any problem. We can tell the participants according to that. Otherwise, generally we after like the last 5 minutes of our question answer, maybe 10 minutes or 5 minutes, as per the time permits. So, if you would like to take the question after the talk, then we can also do that.
No, I am okay with if they ask questions during the talk also. In fact, I prefer that.
Okay. So, how was the pandemic situation there now?
Uh, I think now the situation is much better. We don't have like a lot of such restrictions. We had in Sydney, we had quite a lot of restrictions during last year between June to October, and also the number of cases were quite high at one time. Like in New South Wales, I mean the number of cases per days were almost close to 100,000, but now I think it is reduced much.
Okay.
So how is the situation there?
It seems like that the pandemic is over. Actually, the restrictions are not there now, but we are getting some cases for past few days. Like in our campus also, IIT Kharagpur campus, there are 50 cases maybe. So we are now, they are saying that, okay, wear mask and sanitize your hands again. So for the last 2 and 3 months, it was totally normal.
Oh, that's nice. Yeah, I have a lot of friends in the computer science department, like Onimesh, Shourangshu,
Ha ha ha.
Saptarshi. So I mean,
Yes, yes.
I know with a lot of them, and I also collaborated with a lot of them. So yeah, but I don't think, I think this last typically I mean have like this kind of research discussion with Saptarshi, and he has a student Paheli. So and I think Paheli is about to submit her thesis. So but I think last yeah 2-3 weeks we are not having discussion, maybe because Paheli is writing the thesis. So yeah, but I have quite a few like friends in IIT Kharagpur.
Okay.
So you are also doing your PhD, right?
Yes, sir.
And who is your advisor?
My advisor is Dr. Debashish Shamanto.
Okay.
And my co-guide is from SMST. His name is Dr. Nishant Chakraborty.
Okay.
This is I know you from my MTech days. Actually, I was in Jadavpur University then
Okay.
in
How do you
electrical
know me?
engineering.
How
So
do you know
then
me?
TCS R&D actually came to our campus for campusing, and then I heard your name that time.
Okay. Yeah, I have gone quite a few times to both Jadavpur and Shibpur for campus
Hmm.
recruitment. Even I came to
Hmm.
IIT Kharagpur also for campus recruitment,
Oh,
and
okay, okay.
ISI also. So I mean, yeah, I
Uh-huh.
remember. And that time Animesh was like he hosted me, and
Hmm.
also Shaptoshi was also there. So
Acha,
yeah.
acha.
So I hope the pandemic, if it is over, when I go to Kolkata, I'll get a
Yes,
chance to
definitely.
visit IIT Kharagpur again.
Uh-huh.
Yeah.
Then we can like organize offline event, and you can give to, and you can come to the campus and give the talk.
Yeah, surely. I have visited IIT Kharagpur many times. So
Okay.
uh, yeah.
Acha, acha. Okay, sir.
So shall we start?
Can yes, sir. Yes, sir. Definitely. Okay, so welcome you all to today's talk. On behalf of IEEE Student Branch IIT Kharagpur under the umbrella of IEEE Kharagpur section, we are welcoming you to our today's webinar that titled as BBEVAC, a first location sensitive algorithm for a probabilistic behavior-based building evacuation. So today's speaker is Dr. Arindam Pal. He is a senior research scientist, Data 61 CSIRO, and also a conjoint senior lecturer in University of New South Wales, Sydney, Australia. So join me to welcome Dr. Arindam Pal today. So this will be an 1 hour talk, and we are happy to announce that we are also live in our YouTube channel. If you have any question, as our speaker said, that you can ask in the middle of the talk, or you can use the chat box to ask your question, and we can convey the message to our speaker. Also, those people who are joining us through YouTube live, you can also use the YouTube chat box there to ask your questions. Our whole team is monitoring all of the platforms, and your question definitely will be answered. I assure that. And now let me give a short introduction of our speaker. So Dr. Arindam Pal is a senior research scientist at Data 61 in Commonwealth Scientific and Industrial Research Organization, CSIRO. He is also conjoint senior lecturer in the School of Computer Science and Engineering at UNSW Sydney. His research interests are in artificial intelligence, cybersecurity, and machine learning. He works on business and research problems of CSIRO and collaborates with faculty members of universities both in Australia and abroad. He earned his PhD in computer science from Indian Institute of Technology, Delhi. He has over 14 years of research experience in software companies like Microsoft, Yahoo, and Novel. He has published academic papers in reputed conferences and journals and filed patents in various countries like India, USA, and Europe. He is a technical program committee member for several reputed conferences and technical reviewer for many renowned journals. He is a senior member of both ACM and IEEE. Welcome, sir. Now, today I will give the abstract of the talk. Past work on evacuation planning assumes that evacuees will follow the instructions given to them. However, there is ample evidence that this is not always the case. While some people will follow instructions, others will follow their own desires. In this talk, we will give formal definitions of a behavioral based evacuation problem, in short BBEP, in which a probabilistic human behavior model is taken into account when planning an evacuation. We show that a specific form of constraints can be used to express such behaviors. We show that BBEPs can be solved exactly via an integer problem called BBIP, and approximately by a much faster algorithm that we call BBEVA. We conducted a detailed experimental evaluation of both algorithms applied to building graphs through, though in principle, the algorithms can be applied to any graphs, and show that the latter is an order of magnitude faster than BBIP, while producing results that are almost as good as one real world building graph and on several synthetically generated building graphs. So it seems very interesting topic, and I hope that you all will enjoy today's talk. So, and I would like to inform all of you that an attendance form will be floated during the talk. Please fill the form and mark your attendance. So now I would like to give the stage to our speaker. Thank you, sir. Thank you for joining us in a very short notice. And my personal request, I am grateful to you, sir. Thank you. So now you can share this.
Yeah, thank you, Sucheta, for the nice introduction, and thank you also to you and Akashit and the IEEE student branch at IIT Kharagpur for inviting me and give me the opportunity to present my work. So just can you see my screen in full screen?
Yes, sir, it's coming. Yes, will you please change the slides so that we can confirm?
Yes.
Yes, that is visible.
Visible, right?
Mm-hmm.
It is changing?
Yes.
Yes, sir.
Change.
Okay.
Okay, sir. All good.
Okay. Good afternoon, everyone. So this is afternoon here. I think it is morning in Kharagpur. So we have a 4.5 hours difference. So today I will talk about this project called BBEPs, which is a fast location sensitive algorithm for probabilistic behavior-based building evacuation. And this is a joint work with some of my collaborators, whom I will mention at the end of this talk. So before starting the talk, I would like to acknowledge the traditional owners of this land where I am sitting, the Gadigal people of the Eora Nation and their elders, past and present. So, and also I'll be happy to take questions during the talk also. So please feel free to, if you have some questions or you are not understanding something, please interrupt. You can interrupt me and ask any questions, because this talk will be quite technical in nature and maybe quite complex also in some part of the thing. And I'll not have the chance to explain all the technical details. I'll try to give a idea of the whole scheme of things, because the actual working is quite complex. But please feel free to interrupt me, and also you can also send me emails after the talk if you have any questions. So here is the agenda for today's talk. So I'll start with the evacuation planning problem and how we can evacuate people during an emergency from large buildings. And also these ideas can also be applied to other situations, like even in the scale of a city. But for concreteness, I'll concentrate on the building evacuation problem, typically evacuating many people from a large buildings. So then I will go through the concept of weak and strong evacuation schedule. Then I'll describe what is our probabilistic building-based evacuation framework and how we are actually defining it. Then I'll give a brief idea about the computational complexity of this evacuation problem. Then I'll briefly describe the integral linear program corresponding to this weak and strong evacuation schedule. Then I'll go show how we can express the human behavior models using this constant of this integral linear program. Then I will describe how we can solve the evacuation problem with the two algorithms which we call the BBEP and BBEPs. Then I will give some experiments and results that we have done on both real-world building graphs as well as the synthetically generated graphs, and show how they perform on those things. Finally, I will conclude the talk and will give some directions for future research. So why is evacuation planning important? Now, there have been many buildings that have been that needs to be evacuated quickly, and particularly in recent years, maybe last 20 years or so. I mean, before that also it was true, but there are some dramatic incidents that have happened which leads to the evacuation from large buildings. So one example is, of course, the famous 9/11 attack, September 2001, in which the terrorist flew plane to the World Trade Center and the Pentagon. So the Twin Towers. So there are also other buildings that needed evacuation during terror attacks. For example, the Westfield Mall in Kenya and the Taj and Oberoi hotels in Mumbai. So these were also terrorist attack. The I think 2008 Mumbai terrorist attack. In November 2015, at least two major airports, London and Miami, had to be partly evacuated because of fire. Now, this kind of situation, and these are very important to evacuate people in a timely manner because these are life and death situation. If you cannot evacuate them people in a timely manner, most of them will be dead or severely injured. Now, these situations have led to the development of building evacuation models. So they are studied in both the operations research, computer science, and AI communities. So this because this is such a very important problem. But the thing is that one of the problem on all these works is that they are based on the assumption that during an emergency, people will do what they are told to do. Say, for example, by an administrator or the security. But that need not be always the case. So in this work, we don't make that assumption. But since if you have to develop any kind of mathematical model, there has to be certain assumption, right? So instead, we make a different assumption that all evacuees will act according to a certain probabilistic behavior model. And I will explain what I mean by that. So here is an evacuation diagram from a building floor plan. And I'm sure, for example, I was earlier working on TCS research. They had a lot of these evacuation diagrams. And I also actually, when I did this research, I got these things from the building security and the admins. So here also, so I just show one evacuation diagram. So in our CSR also, there are this kind of evacuation diagram. So for example, it shows you are here and here are some exits that you can see and how you can maybe follow some paths in this building and to get out of these exits. So during so suppose there is a fire or a terrorist attack or those kind of things. And I'm sure in your building also, in buildings in IIT Kharagpur, you will have this kind of evacuation document because these are part of the safety and security of a building. Okay. Now, the question is, suppose you are in a building at a particular location L and a fire or terrorist attack occurs. Now you are told to follow a route to an exit EX that you know is further away than the nearest exit NX. So, for example, you come to your office or your class every day, right? And you know which is the nearest exit. The question is, if suppose an algorithm tells you, or even a building security tells you to follow a route to an exit EX, which is further than the nearest exit, will you do so? So most of the time, I mean, existing algorithms always assume that people will follow what they are told to do, but often people don't do that way. So that's what. So past work they show that people will do what they are told and they will select mechanisms that are globally optimal but individually suboptimal. So, for example, people will follow those routes which are good for the whole community but they need not necessarily be good for themselves, right? So but in reality what happens is that humans are typically rational and selfish agents, so they want to maximize the chance of their own survival. They don't really care about what others will do. They just want to like survive themselves, right? So even if an algorithm selects it to optimize the overall good of the all the people, but most people, they are selfish. They will try to choose those options or mechanisms that are good for themselves and not necessarily good for others. So now also there is a lot of importance or significance of the shortest path. So we did a lot of study on this work in firefighting and emergency response. And in this community, they have done a lot of human behavioral study on how people behave during an emergency. And so some of the observations they had was, if you have routes with lot of turns, they are perceived by people to be longer. And also routes which have many intersections, which intuitively is true because we also, if you think about yourself also, you also think that way. You will also think that way. Now also, several studies have shown that if you have a familiar path, for example, the path that you typically follow from coming out from an entry to your desk where you are sitting, typically you will follow that path to go to that entry, which is now an exit, right? So familiar paths are perceived to be shorter than unfamiliar paths. Now, all of these observations suggest that different individuals make decisions that strive to find shortest path according to different definitions of shortest. Now, the shortest not necessarily means in terms of the actual physical distance. It can be based on any other different matrices also, for example. And typically in kind of graphs or thing, we define this in some kind of a distance function, which is not necessarily the in terms of the actual physical distance. It can be, for example, the time taken to be to go there, right? And that it may be possible that a route is longer, but there is a less congestion on that route, so that's why that will be shorter in terms of the time taken. And that we also see on the roads. For example, if you take a longer route, but if there are not many cars on that, that will be shorter actually in terms of time, that will faster. Now, so basically, so we got this problem. Actually, I started working those problems. This was a problem that came to TCS from the building admins, because TCS are many large buildings, and we had to evacuate these people from this in a timely and organized manner. And we used to have this kind of evacuation drills. So, for example, the building I was in Kolkata, that building had about 9 floors, and it had about close to 4,000 people, and there was a mock evacuation drills are going on. Now, if you see, then so they typically will take people to the stairs, and typically in this stair there are a lot of congestions there, because the elevators will be switched off, and then in this stairs there will be a lot of congestions, and that can actually lead to stampede, right? So, and the security or admin, they don't have a very good understanding, because they don't have a global view of the whole building, so they have only a localized view. So that's why I mean we thought that this can be done in a much better manner if you use some kind of algorithms and use some AI to solve this problem, because then you will have a global picture, because the algorithm at its disposal has the whole building, its floor map, and also all the parameters of that building, right, which humans typically don't have. So to implement this scheme, there are 2 aspects of this. One is the sensor part of that, and the other is the algorithm part of that. Now, we mostly, my team, me and my team mostly work on the algorithm part. There was another team which was worked on the sensor part, but I want to describe the sensor part also before that, so that they together make the complete solution. Now, what we did was, in brief, we considered evacuation planning using mobile phones to locate individuals. Okay. Now, so what we did was we installed a system that we called Smart Evac Track. So basically, smart evacuation tracking, and there are 2 types of devices in that smart that system. So the first type of component is we call magnetophens, which uses electromagnets that are deployed on the floor to detect entry and exit of smartphones. So if a person's mobile phone is in close proximity to the person, so he can be accurately tracked. Now, of course, we assume a person's mobile phone is a proxy for that person. So, for example, if you keep your phone on the desk and go somewhere else, I mean, we cannot really track, because we need some kind of electronic device to track you, right? We cannot track you as a person. We need something. So either you have to have wear a sensor, or you have to have a mobile phone. So we assume that if there is a mobile phone, that is the location of the person. Again, that's an assumption. Sometimes that may be wrong, because maybe you have put your phone in your desk and go to the kitchen, or maybe gone outside for playing. So there is a chance of mistake, but most of the time we keep our mobile phone with us. So that's why this is the assumption. And the second component, the zone Y component, it uses the receive signal strength indicator, shortly RSSI, to identify the signal strength of this mobile phone. Basically, we use the mobile phone, and typically they connect to their the wireless router. So there is a way to triangulate these things, and we can figure out exactly where, with of course some margin of error, we can figure out where a particular mobile phone is located. So that is using the RSSI technology. Now, because RSSI is, so there are, again, as I said, there are 2 parts of this whole complete system. One is the sensor part, one is the algorithm part. In this, I'll of course develop mostly the algorithm part, but it is good to have the context of the sensor part also, because the sensors provide the data that the algorithms will process downstream. And again, after they make a decision, they will again give that path to the same sensors, in this case, mobile phone. So it's important to have the overall picture in mind. Now, because RSSI is very cheap, so we believe that it is very feasible to deploy this kind of a solution. So, for example, a smart evacuator does not use RFID in order to provide a very cheap solution, which cost about $10 per door. Okay. So suppose consider a shopping mall which has 500 stores and each having 4 doors. Then it will cost, so there are 200 doors and each with $10, it will take about $20,000 to equip, which is very cheap for a shopping mall. Typically also millions of dollars, right? Maybe they will about maybe $20 million. For them, $20,000 is nothing. I mean, to deploy this kind of technology. So henceforth, we assume that such a tracking system exists that we want to in the building that we want to evacuate. And also, I already said that we assume that the location of a person's mobile phone is a proxy for his or her location. So we have these two assumptions in mind, and then we'll show how we can design algorithms where we can do track a person and based on his or her location and the capacity of the building, we can evacuate them. So any questions till now? Okay, so now,
no, sir.
Okay, so here are some of our contributions. So we provide a very general definition of an evacuation behavior model that capture past work as well as many other kind of behaviors. And I'll give two concrete behavior model to show that our definition of a behavior model is very general. And also we do put it in a very strong theoretical foundation. So we prove that the problem of deciding whether it is possible to evacuate at least K people by a given deadline D in the presence of a behavior model is NP-complete. So this problem is really quite hard. So there is not much hope to solving it exactly. So instead we'll try to solve it approximately. We'll also show that we can express many evacuation behavior models using a set of constants for some integer programs. And I'll show you how we can do that. And in particular, we illustrate two concrete behavior model. One is the nearest exit that I talked about, and I'll describe in details. And one we call the delayed behavior model. And we'll design two algorithms for doing that. And then we'll show detailed experimental evaluation of these both algorithms on building graphs and show that BBEP is an order of magnitude faster while producing similar quality results. Of course, it cannot be exactly as good as that because it's an approximate algorithm, whereas BBEP is an exact algorithm, but it will come quite close. And we'll see how. So now let us start with some of the fundamentals. Okay, so how can we design such a probabilistic behavior-based evacuation framework? So in this, so suppose P is the set of people in a building that must be evacuated. So maybe suppose there are 5,000 people, and so P is the set of these people. So T is the set of all time instances. For example, if you are running this kind of evacuation for 10 minutes, so T can be in terms of second, it may be 600 seconds. So T max is 600. Now, evacuation planning starts at time T equal to 0 and ends at T equal to T max. So then this is the time between which it is running. Now, to run all this, so we need a frame, a setting, right, on which to run. In our case, that setting is a building graph. So a building graph G is basically a set of a tuple where V is a set of vertices, E is a set of edges, C and D, C is the capacity function and the D is the travel time function. And EX is the set of exits. So I think many of you are familiar with the terminology of graph theory. So these are quite well known to, but at least V and E. Now CV is basically the capacity of vertex V and C is the capacity of edge E. And D is the time required to travel on the edge E. That means if you are on one endpoint, suppose that edge is UV, if you are on one endpoint U, and then you take D amount of time to go from U to V. For example, maybe if it is D is 10, that means you've got 10 seconds to go from U to V. Okay. Now, if a person reaches some exit, then he is safe. Okay. And we assume that the capacity of every exit is sufficient enough to hold all the people. So that's why CB is greater than equal to cardinality of P. So each exit can hold all the people. So anytime a person reaches one of the exits, then he or she is safe. So here is an example of a sample building graph to illustrate this concept. So square nodes here are the exits. and the uh, circular nodes are the normal nodes. So just to distinguish them. Now, in every vertex, you have the vertex label. So the first label shows the name of the node. So for example, V1, and the second shows the capacity of a node. So basically, in this case, V1, 2 means V1 and 2 is the capacity of V1 or CV1. And similarly, age labels denotes the capacity and travel time for the age. So for example, if you are going from V1 to V2, it shows 2, 1 in that age. That means that that age has a capacity 2. So that means at most 2 people can go through that corridor at a time. So that's the capacity. So the ages represent basically corridors in a building, right? And the vertices are the rooms. So 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 you require 2 people can go together at most at a time, and the time required will be 1 unit. So maybe 1 second from going from V1 to V2. And the percents are on this vertices, like P1 is on V1, P2 was V2, like that. And there are 2 exits, EX1 and EX2. I hope this setting is clear. It's quite simple actually. Now then we can come to the notion of what is known as a state. So basically a state is a mapping from the set of people to the set of vertices and union edges. So in simple term, that means that given a person P, a state will show where each person is at some fixed time point. So it is the state of a person at a given time point. Note that at a given time, a person can be on a vertex or an edge. So in terms of buildings, a person can be either in a room or within a corridor, right? These are the only 2 possibilities. So for example, figure 2 shows a state of S at time t equal to 0 when the evacuation planning starts. At that point, this is the situation. So P1 is at the vertex V1 or room V1, P2 as V2, like that. So in this case, all of them are on some vertex or room, but they can be also on some edges. So this is just an example. Okay, now this state tells us that the people P1, P2 up to P7, they are located at these vertices respectively. Okay, so that is a state. So S of P1 is equal to V1 and S of P7 is equal to V10, as you can see in the figure. Now suppose P1 starts moving from V1 at t equal to 0 towards V5. Now note that for the age E equal to V1 to V5, the travel time D is equal to 2. Okay, so at t equal to 1, he will be on E because he requires 2 units of time to reach from V1 to V5, and after 1 unit of time, he will be on that edge E, which is connecting V1 to V5. But at t equal to 2, he may reach the vertex V5, or he may choose to stay on edge. He may not, after 1 unit, he may not even want to move from that edge, right? But he can either reach from V5, or he may stay on, come back, stay on E, or he may even come back again from that edge to V1. But the important thing is that after t unit of time, if he wants, he can go from V1 to V2, because that is the travel time from V1 to V5. Okay. Now, to model this problem, so now note that this problem has certain constraints that needs to be satisfied to get a feasible solution. And that a feasible solution is one where you will get where you will be able to evacuate those people from their respective places, either from their rooms or the corridors or vertex or edges to some exits. Okay. So there are mainly 2 constraints that any evacuation planning algorithm must satisfy, and it is not just our algorithms. It is any evacuation planning algorithm has to satisfy these 2 constraints. So suppose to describe that, suppose these constraints, suppose OTV and OTE, these are the number of people occupying the vertex V and edge AG at time t respectively. Okay. Now the vertex capacity constant says that OTV is less than or equal to CV. So at any time, the occupancy of any vertex must be at most its capacity. Similarly, the H capacity constant says that OTE is less than or equal to CE. That means the similar occupancy is less than or equal to the capacity for an AG. So these are the vertex and edge capacity constant. So together you can call them capacity constants. And the exit constant says that the summation of OEX and OT max should be greater than equal to P. In English, that means that every person must reach some exit by the time P max. Now, these two constants must be satisfied for you to say that I have evacuated, we have evacuated all the people successfully. Now, we come to the question of evacuation schedules. So, suppose an evacuation schedule is basically a sequence of states which is capturing the positions of the people for each time interval t. Now, we define two types of evacuation schedule. One we call weak and the other we call strong. Now, what is the difference? So a strong evacuation schedule is one that can actually be executed, whereas a weak evacuation schedule may not be executable as they may not satisfy capacity constants or exit constants. So recall that there are two constants here. Actually, there are three constants, but vertex and edge capacity constant, they are of the type capacity constant, and then there is exit constant, right? So that's why I said two. Now, maybe although our goal is to generate strong evacuation schedule which are feasible, so they satisfy all such constants. Recall I said that the evacuees are not they will not always follow whatever they are told to follow, right? They will try to behave erratically and they will try to they will try to optimize their own chance of survival, right? They may not be able to care about others. So it may be happen that they may violate some of the capacity constants. For example, there is a corridor during which only 2 people are supposed to go, but then maybe 5 people will go there, right? Because they want to go to the nearest exit, and in the process they may cause a congestion and stampede, right? So they may violate those constants. So, and you may not have control over that. So, for example, overcrowding, I said. So this is the reason why the concept of weak evacuation schedules are needed. Now, here is a more formal definition of that. So I'll not go through this in detail. Though I have written that, I'll not go through the exact mathematics in detail. I'll just tell in English language what they means. So suppose ST is a set of all possible states. So then a weak evacuation schedule is a mapping which satisfies these constants. So that's why I have also written by a triangle. In English, it means that if a person is on a vertex V1 at a time t, then at time t plus 1, he will either stay on the vertex V1 or moves to an edge incident on V1 or an adjacent vertex V2. So these are the only three possibilities. Similarly, if a person is on an edge E, which is V1, V2, then at time t plus 1 in the next time instant, she may either be on E or she may move to one of the endpoints of E. So that's the only possibilities. The third one is if a person is on V1 at time t, then he can reach an adjacent vertex V2 only after the travel time D. That's a constant, right? Before the travel time, suppose D is 5, he cannot reach the adjacent vertex before the travel time D elapses, or maybe that time 5 elapses. So I need that much time to move to the next vertex. And the fourth condition is that if a person reaches an exit at some time point, then she cannot leave the exit. Of course, she don't have to leave the exit, right? Because that was our destination, goal to go reach to an exit. And there she is safe. So why should she leave that exit, right? So these are the four conditions for an evacuation schedule to be a weak evacuation schedule. That is a constant that needs to satisfy. Now here is a weak evacuation schedule that I have shown on for that particular graph, the one which I showed earlier. So you can see that on the first column is the percent, so for P1 to P7, and then so WSP10 means the so for the percent P and 1 is the one on top is basically because it's for WS1 and 0, 1, 2, these are the time intervals. So for at time t equal to 0, time t equal to 1, t equal to 2, like that. So what is the state of that person, where that person is? Either he is on a vertex or she is on an edge, right? So these are the situations. Now note that here, rho represent the evacuation schedule. Between t equal to 1 and t equal to 2, if you can see P3, P5 and P6 are crossing the edge V10 to V7. Okay, here. Now, but its capacity is only 2, so they are violating a capacity constant. Now, but in this case, all of them are reaching to some exit by time t equal to 4. So for this particular evacuation schedule, the capacity constant is violated, but exit constant is satisfied. So that's why it is weak, because it is not satisfying the capacity constant. Okay. So I show another weak evacuation schedule. In this case, you will see that the capacity constant is not violated for any of them. You just have to check that if you run through this. But P1 does not reach any exits, but stops on V9 after passing through V2. So in this case, the exit constant is violated. So the reason why I showed two different evacuation schedules is that one violated the exit constant and the one violated the capacity constant. So WS2, for example, violates the exit constant, but it satisfies the capacity constant, whereas WS1 did the other way around. So for one of the two reasons, they can violate this and they can be weak. They are not strong. Now, before proceeding, here are some thoughts on weak evacuation schedule. So, for example, weak evacuation schedule may violate capacity constraint and then they can fail to move all the people to an exit. So they always exist. Weak evacuation schedule, I mean, there is always, for example, the trivial thing or the stupid thing to do, that the schedule where no one moves from the initial position, that's clearly a weak evacuation schedule because nobody reaches to an exit. So they violate that, but it's still an evacuation schedule. It's a trivial weak evacuation schedule, right? So that shows that weak evacuation schedule always exists. Now, but our goal is not to find weak evacuation schedule, but to find strong evacuation schedule. So basically, a weak evacuation schedule is strong. It will satisfy the following additional constant. The first constant is that the number of people on a vertex cannot exceed its capacity. That is basically satisfies the vertex capacity constant. The second is that the number of people on an edge cannot exceed its capacity. So it satisfies the edge capacity constant. And every person must reach an exit by the time T max. That satisfies the exit constant. So basically, a strong evacuation schedule respects all vertex and edge capacities, and every person must reach an exit by the time T max. So that makes it a strong evacuation schedule because it now satisfies all the constants. So here is an example of a strong evacuation schedule. So if you work out this example, I mean, on the building graph, of course, I don't have the time to exactly go through all, but you can do at your own time, and you can actually verify if you go through all these things that every person reaches some exit at time point t equal to 4, and none of the capacity constants are violated. So this is a strong evacuation schedule. So now this is all about the two different kind of evacuation schedule. Now, what is a behavior model? So we define the behavior model in the following way. So suppose S and W are the set of all strong and weak evacuation schedule, and PW is the set of all probability density function. So basically, what is a probability density function? It's a function omega such that summation of omega is equal to 1. So basically, this is the standard definition of probability, right? So and that makes it a PDF. So suppose W omega is the set of all weak evacuation schedule such that the probability mass here W omega of WS is at least strictly greater than 0, because if it is 0, then we may not even include it. So basically, a behavior model is a function which associates a PDF omega over the set of all WSs with each ACS strong evacuation schedule ES. So just to this definition may sound complicated, but it's really simple, the idea. So suppose consider this ACS ES and the two weak evacuation schedule WS1 and WS2. Now suppose the capital S is the set ES and the W is that WS1 and WS2. Now here is a behavior model. So a behavior model beta, they will map PS to the PDF such that omega of the WS1 is 0.2 and omega of WS2 is 0.8. So basically, given that small evacuation schedule, the weak evacuation schedule WS1 will happen with probably 0.1 and WS2 will happen with probably 0.2. So that is what it means. Though it looks like a complex thing, it's simple actually. Okay. So any questions till now?
Yes, sir. We have some questions from our YouTube channel. One participant said that very nice talk, very informative. It is an interesting topic. Do I need to study graph theory if I want to work on this field?
Yeah, definitely. You have to know quite a lot of things about graph theory and combinatorial optimization to work on that.
Okay, sir. And another question is, what is the real life implementation of this algorithm? During an emergency, do we really follow any evacuation plan?
No, that depends on in most of the places there is no evacuation planning program or most like for example I have seen most of the like Indian like offices. I mean there is no such thing. Right? It's manual. So that's why we want to do it in a much better way, right? Using an algorithm to guide us to that. And I'll show you how this gets much better compared to if you do it manually versus we do it with algorithmically. You get much better solution. Okay.
Okay. Another question is, sir, is there any software available to solve contraflow evacuation planning problem?
What does it mean by contraflow?
I don't know, sir. Someone asked. Aditya, if you are here, you can ask the question to sir.
Okay, maybe I can take it at the end. I mean, let me continue.
Okay,
and
sir.
then, okay.
Yes, sir.
So basically, let us have some thoughts on like this behavior model. So what is a behavior model? So now it tells us, suppose you have a pair ES and beta ES. So it tells us the probability. Suppose the system tells users to follow the strong evacuation schedule ES. So what is the probability they will instead end up following the weak evacuation schedule in beta ES with the corresponding probabilities? For example, in this example, suppose the system has generated the strong evacuation schedule ES, and what is the probability that WES1 will be followed? That is 0.2, and WS2 will be followed is 0.8. Okay. Now, because evacuation is again they are selfish and rational agent, right? So they may act out of their self-interest and they may not consider about the overall evacuation plan. Their behavior in general leads to a weak evacuation schedule. It may not be strong. Now a behavior model tells us what the expected behavior of the evacuation population would be if they are told to follow a given strong evacuation schedule. So that is really the behind the idea and the concept of a behavior model. How do I map them from the weak from the strong to the weak evacuation schedule? Now, so we define an evacuation framework, which is basically a triple G S naught B. G is a building graph, S naught is the state at time t equal to 0, and beta is a behavior model. So, for example, one example that we showed in figure 2, this is the behavior model. So, we'll show that both the nearest exit behavior model as well as the where the evacuees try to go to the nearest exit, and the delayed behavior model where the evacuees follows the suggested evacuation route with the delay, they both can be expressed within our framework, and many others also, but we'll just show only these two. So now I want to talk a little bit about the hardness or the complexity of this program that we showed. So suppose given a strong evacuation schedule or maybe weak, the number of people that are evacuated by D is basically this quantity NEST, which is basically the number of people that have been taken to the exit by the algorithm. And in this case, if in the presence of a behavior model, because now this is a probabilistic solution, right? So you cannot really talk about because in different instances you can have different kind of things. So you talk about the expected number of PABL, expected number of people that are evacuated by the deadline D. So that is basically E expectation of NEST, and that is given by this thing. So basically you are computing a mathematical expectation. So now we did formally precisely define this evacuation problem. So the evacuation problem is given an evacuation framework and a deadline D, find a strong evacuation schedule ES that maximizes the expected number of people evacuated by the deadline D. So which is basically expectation of NESD. And also we can study the decision version of the evacuation problem, which is that given an evacuation framework, a deadline D and the number of percent, we have to decide if there exists an ACS ES such that this expectation is at least K. So can we, in expectation, the expected number of people that we evacuate, is it at least K? So that is the decision version of the problem, and that the earlier one is the optimization version. Now we prove a couple of results about this computational complexity of this. So the first theorem that we have is the DEP. The decision version is NP complete. So we show a reduction to this DEP from the NP complete problem, simple undirected two commodity integral flow. So this is a known NP complete problems, and basically you know the way how do you solve show NP completeness. You typically do a polynomial time Turing reduction from another NP complete problem, and this is about 2-page long. I mean, it's quite complex, so I'm not talking about the details, but this is we have proved. And the corollary of this theorem is that the EP problem, the optimization problem, is NP hard, even if like this all the capacities are 1, and at the initial state all the people are located on at most 2 vertices, and this is over a single PDF. So what this technical condition really show is that even for very special instances, very special cases of the evacuation problems are very hard. Even if you have the unit capacities, and even if all the people are on just 2 vertices, so for such a simple instance also this problem is very hard. Of course the general problem will be much harder, but this shows that for a very special classes of graph and very special classes of settings, this is very hard. Okay, now I don't know. Okay, I have 15 minutes, so I'll now quickly go through that. I cannot give the. So here is a integral linear program for these WS and ACS. So of course I cannot go through all the details. I just want to mention that the weak evacuation planning part that has a integral program LPWG that corresponds to this constant 1 to 8, and the strong part that has the additional constant 9 to 11. Okay, so LPS WG is 1 to 8 and LPS G is 1 to 11. And of course, I don't have the time to go through the details how to explain how this thing works. And also, I mean, to understand this, because it's a quite complicated integral linear program, so you need this kind of a gadget to explain that thing. But again, I don't have the time to go through in details because it will take quite some time. So I'll skip that. Just I want to see how do you explain this integral program. Now, again, so you can show, now suppose I have written an integral program, right? So you need to show that the weak evacuation schedule and this integral program, they correspond precisely. There is a one-to-one correspondence between those two, right? So that we show using this proposition 1, we show that given a weak evacuation schedule that corresponds to the solution of this LPWG, and conversely given a solution of this LPWG that corresponds to a set of weak evacuation schedule. Again, I don't have time to go through that or prove or give some intuition, but just I want to state that there is a one-to-one corresponding between this. Similarly, if you see the ACS and the LPC study, there is also similar correspondence, and all this we have proved in our paper. So if you are interested in the details, you can send me an email and I can discuss how we can prove this kind of results. Okay. Now, basically, so how do we express the behavior model with constant? So the integral linear programs above, they don't take behavior models into account. Till now, they are only using the normal inter. Now, in addition to this constant, we have to express the behavior models. Now, to express that, so that also requires quite a lot of kind of technical machinery. So basically, the idea is to make k copies of these integral programs and then stitch together in a I'll not say in a simple way. It's quite involved. So the idea for this is to describe these things together and then stitch together in a specific manner. And then again, I don't have the time to go through that, but we can discuss this if anybody is interested in the more technical stuff. Okay, and then you can define this thing using a particular type of syntax to express all this behavior model, and this is a very general way of representing the behavior models. Again, I am not going through what is the correspondence between all these theorems, but instead I want to go through two concrete behavior models that can be expressed in our framework, and many others also, but I want to show these particular two. Suppose um, the system communicates to all people in a building that that you have to evacuate and follow this thing. The delayed behavior model says that everyone follows this weak evacuation schedule with a delay of tau I with probability alpha. So, for example, it tells the person P1 that you follow this particular behavior, schedule with a delay of 5 seconds and with probability 0.2. The second one, you follow this with a delay of 10 seconds with probability 0.3, like that. So that's the delayed behavior model. And it's a very natural behavior actually during an emergency. Now, one thing, the problem is that how do we estimate these probabilities? So that's the challenge. So typically these are done by from the periodic evacuation drills that you can do. So these statistics can be obtained from such drills. And the other model, which is also quite natural behaviors during an emergency, and this you have seen, is that suppose you are given a person to follow a path suggested by the evacuation schedule. So they will follow this particular path suggested by the algorithm with probability alpha, and they will follow the shortest path from the vertices they are present to the nearest exit probability 1 minus alpha. For example, suppose I am given, the system tells me you follow to go to this exit E1, but my nearest exit is E2. So with probability maybe 0.3, I go to the exit suggested by the algorithm. With probability 0.7, I go to the nearest exit. So that is the behavior model. Okay. Again, in this case also, determining alpha can be challenging, but it can be obtained from a series of regular evacuation drills by counting how many people go to the nearest exit and how many follow the instructions. And from there, you can get an aggregate. Suppose 3 people go to the nearest exit and 7 people go to the actual exit suggested. So you can say it is 0.3 probability to go into the nearest exit and 0.7 probability going to the exit suggested by the algorithm. So you can actually, there are ways to find this out. Now, we designed 2 algorithms, different algorithms for. One is BBEP, which solves this using integer programming. The other is BBEPs, which incrementally solves this evacuation problem for subgraphs of the building graph, which we call exit graphs, by taking the behavior model into account. And what we do is that basically we define what is known as the projection of the behavior model on this exit graph. Okay, so you can think of, because you have studied in a computer science a divide conquer method, you can think of this in some sense as some kind of a behavior, a divide and conquer algorithm, but it is quite complex and sophisticated to make this divide and conquer work. Okay. Now the question, because BBEP is an integer programming solution and it's solving this NP-complete, it is unlikely to be efficient because you cannot solve an NP-complete problem in polynomial time, right? So whereas BBEP is much more efficient, but it gives an approximate solution. So again, I will not go into the details of the BBEP and BBEP because we don't have enough time. I just quickly want to mention that kind of things we involve. So these are the kind of hardware we used and the libraries we used. And so we ran experiments on the EcoSpace building in which we worked. I mean, in the TCS building. So the statistics of this building is it have approximately 3,000 employees, and it was modeled as a graph with 133 nodes, 200 edges, and 2 exits. Now for each edge, we computed the distance and capacities actually estimated manually. We actually went through walking the thing and based on the stopwatch, and we actually found out what is the distance and the capacity. So this building we called it EcoSpace dataset. And also we ran experiment on 840 synthetically generated graphs. And we created these graphs using the NetGen software from the Technical University of Vienna. So this software actually can generate synthetically generated graphs. Now we simultaneously varied the number of nodes, edges, exits, and people. So in this manner, it's like number of nodes from 110 to 200 in steps of 10. Number of edges was like from 1.35 to 1.7, number of nodes like that. Okay, and for a given number of nodes, we generated 84 graphs and 120 graphs for each population size and 140 graphs for each deadline and average. This always we took the average of this thing, right? So this led to a total of 3,360 evacuation planning problems, and both of them were analyzed under DBM and NEBM, both the behavior model. So here are some results that we have got. So we did a lot of study of these things. So first we study the runtime of this as the number of nodes varied for DBM and NEBM. You can see that BBEPs is blue and BBIP is red. So the runtimes of BBIP is much higher than the runtimes of BBEP for both the instances, for DBM as well as NEBM. So this was runtime was varying as the number versus number of nodes. When you vary runtime versus number of evacuees, you can see that similar kind of behavior. In this case, actually the BBIP is getting much higher the runtimes in terms of second, maybe 6 times or more, and the other one is 3 times or more. Now, when we write runtime versus deadline, we also have similar behavior. So it is clear that always BBIP is taking much longer time. Maybe the ratio is varying, but it's clear that always it is taking much longer time. And that is expected, right? Because that's an integer program that is trying to solve the problem, and it's not a polynomial time algorithm, so it cannot really scale. And runtime versus deadline for a real building graph, you can actually see that for a really large building graph, it cannot even. So, for example, see, you cannot get any red line. So not beyond this point, because the algorithm, I think we put about 2 hours or so, it did not even complete in that. So it cannot really complete in a reasonable amount of time. Whereas BBEPs is actually able to complete that. Now look at the number of people evacuated versus number of nodes. Okay, now you see that the BBEP is, of course, because it's not an optimal algorithm, whereas BBIP is. So BBIP is obviously able to evacuate much large number of people, but BBIP is actually able to evacuate a large fraction of the people that BBIP is evacuating. And similar kind of trends you see as you vary the number of people evacuated versus number of evacuees, deadline, and also for the eco space. Because for the eco space, you can only vary deadline because the graph is fixed, right? So you cannot change the number of nodes or the number of edges. So as you can see, many times BBIP is not even able to finish, whereas BBEPs is able to get good results. So in summary, we get for synthetic graphs on average. So this is our observation. We did a lot of study. We did all the analytics of that for the average and see what is happening, and then we summarize this result, and this has the summary. So for synthetic graphs, on average, BBEP takes only about 10 to 20% of the time taken by BBIP for both types of behavior model. Whereas BBIP takes 60 to 120 minutes, which is 1 to 2 hours. Now for EcoSpace, when the deadline exceeds 270 seconds, BBIP is unable to complete within 30 minutes for DBM or NEBM. When BBIP completes, it takes 10 to 30 minutes. But BBEP always completes even as the deadline increases. Now for synthetic graphs, BBEP evacuates 80 to 90% of the people evacuated by EBIP. For EcoSpace, BBEP evacuates at least 85% of the people evacuated by BBIP. Now the thing is that in a real building evacuation, see, I mean, first you have to compute the evacuation path, then you have to evacuate that, right? So if waiting for 30 minutes to generate an optimum plan is not an option, because by that time most people will be dead. So you have to, what you have to do, you have to run a fast algorithm, which is location sensitive, and then you have to evacuate this. So the time taken for the evacuation is the time taken to generate the plan to run this algorithm, plus the time taken for the actual evacuation. So in most of the cases, if you try to solve an optimum solution, you may be able to generate an optimal solution, but it will not be useful because by that time, most of the people will be dead. So to conclude this talk, so first is that observation that we observed is that people do not necessarily behave as instructed during an evacuation. Now in this work, what we try to do is that we try to develop an abstract mathematical definition of a behavior model in an evacuation situation. We showed that maximizing the number of people evacuated by a deadline in the presence of such behavior models in NP-hard. We also showed that in many cases, this kind of abstract mathematical definition can be expressed by a set of constants of an integer program. And to illustrate that, we present two concrete behavior models the delayed behavior model and the nearest exit behavior model, and showed that they can be modeled in our framework. Then we presented the two algorithms BBEP and BBEVAC to maximize the number of people, and we constructed a comprehensive set of experiments by varying different quantities of the different parameters of the graph as well as the deadline, and showed that BBEP performs much better than BBEP in real life, while doing the evacuation and taking only a much lesser time compared to BBEP, while evacuating say 85% to 90% of the people. So here are some future research direction. So first of all, learning real-world behavior model during building evacuation is a significant challenge. So we tried to propose one type of way of modeling this, but this may not be the only way. I'm sure there are other ways of doing that. And also think of that: how do we get those parameters, right? So in our case, for example, in EcoSpace, we used to have this. Typically, it will be done in every quarter. So that means one evacuation drill in 3 months. So in a year, we'll have 4 evacuation drills, right? So, I mean, I cannot just say that I'm designing an evacuation planning algorithm, so we should do this kind of drill every day or maybe every 5 days. So nobody will want to do that because it hampers our progress, right? In fact, that day we used to have evacuation planning. We are quite unhappy because the whole process used to take like almost 15-20 minutes to get down to the like in the downstairs, and then again maybe 15-20 minutes up, and then you stay there. It can easily take maybe 1 hour, right? So that disrupts our work. So neither the building administrator nor the employees are willing to conduct this thing repeatedly just to get some parameters of our algorithm, right? So how do we do that kind of thing? So these are some of the research challenges. Then how can we set up a framework to test hypotheses about real-world human behavior during building evacuations? So see, I mean, this is still a model, right? So based on the previous observations and previous papers and the behaviors, we have tried to build a model. But how do we really test the hypothesis that this model is correct, right? I mean, so that's the research challenge. So it requires a lot of human behavior analysis, psychological evaluation to find out, for example, whether this nearest exit, how many people actually use the nearest exit, right? I mean, that needs to be evaluated, right? So what other concrete behavior models can be expressed in our framework? So that's also, we showed two, three we can express, but there may be other behaviors which we may not be able to express. So what are the behavior models that we can express? So is there any other general behavior model which can accurately model realistic behavior of people during an emergency, right? We are not aware of any such models. That's why we try to develop the first model using this kind of a mathematical framework. But is there any other kind of general behavior model which can model human behavior? So can we use some ideas from game theory to model user behavior? So that's a very promising approach. So one of my friends told me that maybe you can try to use game theory to model this thing. So that we are thinking if we can do this. And also, can we design an algorithm better than BBEPs in terms of both running time as well as the quality of evacuation? So there is no reason to believe that BBEP is the best one, right? It's possible that there are better algorithms in terms of both running time and quality of evacuation, means the number of people evacuated. So I would like to thank my academic collaborators who with whom I worked with it and for their help and support. So the first is Miss Shubhra Mojumdar. She is a PhD student at Indian Statistical Institute, Kolkata, and she I think almost finished her PhD, and I think she is about to write her PhD thesis. This work was when she was working with me in TCS research, and when we were working this problem. Then Professor Francesco Parisi from the University of Calabria in Rende in Italy. So I had a really nice interaction with both Francesco and Professor V.S. Subramanian from Northwestern University in Illinois, USA. That time V.S. was in University of Maryland, College Park. And I had a lot of discussion with Francesco and Subramaniam. So at that time, of course, we did not have the pandemic, but even before that, we had a lot of Skype calls. Like I think VS was in Maryland in morning, Francesco was in Italy in his noon or afternoon, and I was in the evening after coming back from office. And we had a lot of discussion over more than a year to develop these ideas. And I also visited Francesco for some time in University of Calabria and worked with him closely. And I really learned a lot of them from them. And these ideas would not have come without the ideas and the stimulating intellectual discussion with them. So it is really a global collaboration between Australia, India, Italy, and the United States. So thank you very much for attending to my talk. And if you have any questions, please feel free to ask.
Thank you so much, sir, for such informative talk. Participants, if you have any question, you can ask to our speaker directly, or I can convey the message if you are not feeling to ask directly. So we have some question here, like should we apply different algorithms according to the capacity?
Sorry?
I think should we apply different algorithms according to the capacity? I think the capacity means the capacity of building or something. Like
you mean the edge capacity or the vertex capacity?
So I don't know. I think he just want to ask that the capacity of the building, like if there is 500 people or 1,000 people, should we apply different algorithms for 500 people and 2,000 people, like that?
Oh no, I don't think that should be the thing, right? Because you have to have a general algorithm which should be able to take into account all possible things. You cannot have like different algorithms for different things, right? So when you design, for example, yes, when you have a shortest path algorithm, right? You that's a general algorithm that should be able to handle whatever the edge length may be or the graph structure may be, right? So I don't think you can have say that for different. If the number of people that has to be evacuated is different, then you have to have another algorithm. So it has to be a general purpose algorithm, right? And both our algorithms are general purpose.
Yes, sir. So I hope you got your answer. And another question is, sir, is there any data set available publicly online which we can use for evacuation planning problem?
So for our evaluating our algorithms, we had to collect all this data set manually. So basically, what we did was we TCS had a lot of buildings in. So many of them we got from the TCS Kolkata, but I also got some of the building floor plans from the TCS Delhi and Chennai and Bangalore offices also. So most of the time it was the floor plan and some occupancy data we have got. There is, at least at that time when we did this, there was no publicly available evacuation data sets. I mean, in fact, in other papers also, we said that the authors collected their own data sets. So there was no publicly available data sets where you can run those evacuation algorithm. But it may have changed in recent years. Maybe somebody has built, maybe, I don't know, maybe in Kaggle or some places, this kind of evacuation planning data set. But this one was like, we need a lot of time to build our own data set because we have to get this from the building administrator as well as some of the parameters we have to evaluate. As I said, that we just walked around the corridor to get those times.
Okay, sir. Another question he has asked that can we make an algorithm combining the building and behavioral model for evacuation planning?
So that's what we have done, right? I mean, we have the building is captured by the building graph, and on top of that we have the behavior model, right? So the behavior model is giving the mapping between the from the strong evacuation schedule to a set of weak evacuation schedule, right? So this is like so this takes into account both the structure of the building as well as the behaviors of the people. So our that's what exactly what we are doing.
Yes, exactly. Another, sir, are the codes for algorithms are available on GitHub somewhere else?
No, we have not yet uploaded to GitHub, but we are thinking about making it open source. Yes, definitely.
Okay, so that's all from this side. Other participants, if you have any questions, you can ask. In the meantime, sir, I would like to take a group photo with you, like with the volunteers and the participants who would like to join. So I request you to please share your screen so that we can take a layout of the photographs.
Oh, sure. I'll do that. Just a minute.
request Mr. Ajit Bhattacharya to take a photograph with our speaker. And all the volunteers are requested to turn on their camera, as well as the participants who would like to be part of this moment. Please turn on your camera, and with the count of 1, 2, and 3, Akasit, please, or whoever is
Yeah. Yes. Everyone, please turn on your camera.
just wait for it. Let them turn on their camera. Okay. Are we ready? Akasit, are you ready? Let us know when it's.
Sure. Yes, it is taken. Thank you.
Okay. Thank you so much, sir. Thank you for joining us today. It was a informative talk, and during this pandemic, and when the world is actually suffering from this kind of things like pandemic, the war, I think this evacuation problem is really, really we need it nowadays. So, sir, thank you so much from Australia, and we would like to present you something. Just give me a moment.
Yeah, thank you very much, for inviting me. And I mean, I got a lot of so many people attended and a lot of questions also. And yeah, I think I did not have enough time to answer all the questions. Yeah.
It's okay, sir. So this is the memento from us, as this is an online event, so I can do this much for now. But IEEE student Raj IIT Kharagpur always sent a memento to our speaker, and you will get it in a month. And IEEE student Raj Kharagpur would like to thank you for delivering this technical talk on 4th 2022. So this is a little token of gratitude for you. Thank you.
Thank you very much, Sichada. Thank you, Akashjit, and thank you to the IEEE student branch IIT Kharagpur. I really appreciate it.
Thank you, sir. Thank you.
Thank you, sir.
So, sir, I expect that when the pandemic is over, we'll again invite you on campus, and we can see you in person, and we can listen some another informative talk from you. And thank you for joining us in such a short notice, sir. We're so grateful to you.
Yeah, sure. I'll be able to happy to come to IIT Kharagpur and give a talk in the lecture hall. I mean, that will be really good. And because I like to interact with people, and here also after the pandemic nowadays, I'm going to some of these conferences physically and feel really good to meet with people and interact with them. I'll be definitely very much happy to go to IIT Kharagpur and interact with all of you personally. Thank you.
Yes, sir, that will be a good experience, of course. And all the participants, I would like to thank all for joining us today. We will expect again. And for more talk and events, please follow us on our social media page and website. And I would like to thank again to sir. And sir, thank you. I would like to conclude the session now.
Thank you. Bye, and have a nice day.
Bye. Have a nice day.